SwayamPrabha. Digital India. Educated India.
We are dealing with single input, single output systems, what we abbreviate as SISO, and linear time invariant causal dynamic systems. So that are characterized by linear ordinary differential equations with constant coefficients, right? So that's what we have been discussing. And in the last class, we looked at how one could use the Laplace transform to solve such equations, right? So that's something which we looked at in the previous class. So what we have done till now is to have a broad overview of what we are going to study in this particular course and some mathematical tools that we are going to use, okay? So from today, we'll go into the analysis as far as what we call as the classical control approach is concerned. So one of the main topics that we are going to learn is that of transfer function, okay? So let's see what a transfer function is, right? So let us consider the mass spring damper system that we already looked at, right? So let's say we consider the mass spring damper system that is governed by m x double dot t plus c x dot t plus k x of t is equal to f of t, right? So this is a linear time invariant system, right? So let us take the Laplace transform on both sides. Okay, so what happens if I take the Laplace transform on both sides? We are going to get m times, what is the Laplace transform of the second derivative? We are going to get s squared times x of s, right? Minus s times x of 0 minus x dot of 0. That is the Laplace transform of the second derivative, plus c times s times x of s minus x of 0, that is the Laplace transform of the first derivative, plus k times x of s, which is going to be equal to f of s, right? So that's what we are going to have. Okay, so now if I just rearrange the terms, let me do it carefully. So if I do this, right, so I collect the terms involving capital X of s, okay, I am going to get ms squared plus cs plus k, and let's say I take all the initial conditions to the other side, right? So what's going to happen is the following. So I am going to get ms plus c times x0, right, plus m x dot 0, right? So that's what I am going to get as far as the initial conditions are concerned. Then we are going to have the inhomogeneity, right? So f of s, the force term, correct? So that's what we are going to have. So if I now divide both sides by ms squared plus cs plus k, what I am going to get is the following. So ms plus c x0, right, plus m x dot 0 divided by ms squared plus cs plus k plus 1 divided by ms squared plus cs plus k multiplying f of s, correct? So this is what I will get if I just take ms squared plus cs plus k to the other side, okay? So we already discussed that, this is the component of the output, due to the non-zero initial condition, right? So if there exists any. So if you consider the mass spring damper system, if we view it from the perspective of what we are considering in this course, the input is essentially the force F of t. The output that we are considering, let's say it's the displacement x of t, right? So that is the input, and those are the inputs and outputs, right? So, so essentially, like capital X of s is the Laplace transform of the output variable, right? So, the first term on the right hand side, one could immediately observe that it involves x0 and x dot 0. So that is the displacement which is caused by any non-zero initial condition. So what do I mean by that? Let's say, like I have the mass initially at rest. Suppose, imagine that, like I just grab the mass, like displace it by a small amount and leave it. So I am giving an initial perturbation to that mass, right? So x0 may be 0, x dot 0 may be 0. So the mass may be displaced, and it may vibrate, depending on the values of k and c, and finally it may settle down, back to its original equilibrium state, right? So the first part is the contribution of the output due to non-zero initial conditions, okay? And this, as far as our course is concerned, like we would call it as the free response, okay? So I'm reiterating these points once again, right? So the part of the output, system output, that comes due to non-zero initial conditions is what is called as a free response, okay? And the second part, one could observe that, like it involves the input term, right? Because it's 1 by ms squared plus cs plus k times capital F of s. So that involves the input term F, which is the force. So what does that term provide me with? Suppose if I apply a force, right, a time varying force on the mass, if I keep on pulling and pushing it, with some force, right, what is going to be the displacement of the mass, okay? So that is the contribution of the input, okay, to the output, okay? So due to the input that we provided, okay? So this is what we call as the force response, okay? So that's what is called as a force response, okay? So you see that in the class of systems that we are considering, like we are going to have these two, components to the output, right? So one due to non-zero initial conditions, one due to the input that is provided to the system. Now let's go further. Consider all initial conditions to be 0. Okay, let's consider that all initial conditions are 0. Then what happens in this case? x0 will then be 0, x dot 0 will be equal to 0. Then what would happen to capital X of s? We would essentially have the expression as 1 divided by ms squared plus cs plus k times capital F of s, okay? So this implies that x of s divided by f of s is going to be equal to 1 divided by ms squared plus cs plus k, okay? So if I just take capital F of s to the other side, right? So this quantity, which is the ratio of the Laplace transform of the output to the Laplace transform of the input under 0 initial conditions, is what is called as the transfer function of the system or plant, okay? So in this particular course, what we will do is that, like, we will use P of s to denote this, okay? Just for to avoid confusion with other symbols, like we will use the term P of s, okay? Capital P of s is the plant transfer function, okay? So let me repeat once again. So what did we do? We wrote down the governing linear ordinary differential equation. Then we took Laplace transform on both sides. We saw that the output term has two components, one due to the non-zero initial conditions, one due to the input, right? We took all initial conditions to be 0 there, right? So then whatever was left behind was the component of the output due to the input that we provide. Then we cross multiplied. We took the ratio of the Laplace of the output to the Laplace of the input. Okay, that's what we did. And whatever function in S that we got as a result is what is called as the transfer function of the system or the plant. Okay, which we are going to denote by P of S. Okay, so in general, if we have like for S, if we have the system or the plant, right, to be an entity to which we provided an input u of t and we get an output y of t, right, the plant transfer function P of S is going to be equal to the Laplace of the output divided by the Laplace of the input variable, which we denote as capital Y of S divided by capital U of S, with all initial conditions being taken as 0. Okay, so this is the definition of the transfer function. Okay, so this is something which is very important. Okay, it is the Laplace of the output to the Laplace of the input with all initial conditions taken to be 0. Okay, that is the definition of the system transfer function or the plant transfer function. Okay, so in a certain sense, like when we use the transfer function approach, by and large we are interested in the forced response of the system, right? So that is something which we can immediately realize, right? So because we have taken all initial conditions to be 0. Implicitly, when we are dealing with the transfer function based approach, like we are looking at the forced response of the system, right? What happens to the system output when we provide an input to the system? Now the question becomes, like, would initial conditions be 0 all the time in practice? Okay, not necessarily. Then what would happen if we follow this approach, right? So that's a question we would answer later on. Okay, but first let's continue with our analysis and see where we get to. All right. So of course this is for a CISO system. Okay, like, so please note that we are dealing with CISO. What is CISO? Single input, single output. Okay, so please remember that, right? So only then I can take ratios of Laplace of output and input. If I have multi-input, multi-output systems, what are called MIMO systems, I would have what is called as a transfer function matrix, because I can no longer divide a vector output by a vector input, right? So y and u will become vectors if I have a MIMO system, right? So then I cannot take ratios like this, right? But I can still write it in another form, in a product form, where I can say the vector y of s is going to be equal to a transfer function matrix multiplying an input vector, okay, in the complex domain, right? So that is still something which we can do, but we are going to deal with single input, single output systems, okay, in this particular course. So essentially, this notation holds true for a single input, single output system, right? So consequently, this implies that y of s is equal to P of s times U of s, okay, correct? So that's something which we can immediately get. And this implies that if you use the Laplace, take the inverse Laplace transform, what will be y of t? So we have y of s to be equal to P of s times U of s, right? If we take P of s to be the plant transfer function. So by using the inverse Laplace transform, right? So what do we have? You know, like we have y of t to be equal to integral 0 to t p t minus tau u tau d tau, right? So that's what we'll get as the system output. Okay. So what is p tau? Here p of s is going to be the Laplace of pt. Okay. So we'll see what is the physical meaning of the function pt shortly. Okay. So that is the output in the time domain if we take the inverse Laplace transform. So we can note certain points. So what is the first point? So if p of s is known, okay, so let's say we use physics to derive mathematical models and get the Planck transfer function. Okay, if p of s is known, you know, like we can find the system output for any input. Okay, so please note that. Okay, if once I have the Planck transfer function. Okay, so you give me any input, I can tell you what the output is. And we can do one more thing also. You know, like if I want some output, I can find out what input I have to give. Okay, we can do both. What to say? Control and analysis, right? What we studied as purpose of models, right? If you remember what we studied as purpose of models, you know, like the first step was synthesis, right? In our line of study, you know, like first, you know, like step is to obtain the mapping S, right, which relates the input and the output. In this case, you know, like the Planck transfer function, right, we develop mathematical models. Once I complete synthesis, we can do either analysis or prediction, and then we can do control, right. What was prediction or analysis? You give an input, I tell you what the output is, right. So, and what was control? You know, like I am given an output, I have to find what input will get me that output, right. So that's control, right. So we can do both, you know, like once p of s is known, right. So let the second point which I want you to what to say essentially interpret, you know, from this derivation is that let u of t be equal to delta of t. This is the unit impulse input. Okay. So if u of t is the unit impulse input, what happens to u of s? What is the Laplace transform delta t? 1. Okay, this immediately implies that y of s is going to be equal to, please look at this equation, right. What will be y of s? It's going to be equal to p of s. This implies that y of t will be equal to pt. That's it, right. So if you give any input and you calculate the corresponding output, that output is basically called as a response, and the adjective can be added, you know, which corresponds to the input, that specific input that you are providing. In this particular case, we are providing a unit impulse input to the system. So consequently, the output that we get is what is called as the impulse response. Okay. So for that reason, p of t is the impulse response function. So so what does this mean? That means that I provide a unit impulse input to the system, right, and then, you know, like I find out what the output is, right. So that is essentially what is called as the impulse response function. Okay, and the Laplace of the impulse response function is the Planck transfer function. Why? Because you can see here, right, p of s is going to be equal to the Laplace of p of t. Okay, so that gives us with a very useful idea if I want to experimentally determine the Planck transfer function. Let us say, you know, like I have an experimental setup, you know, like I want to experimentally figure out the Planck transfer function. What I need to do? I just need to give a unit impulse input and then like measure what is the output, and that will be the impulse response function, right? From the impulse response function I can calculate the plant transfer function, okay? But what is the catch here? The advantage is I need to do only one experiment, right? That's it. But the catch here is that like in practice it's very difficult to give an ideal impulse input, right? See, what's an ideal impulse input? One which instantaneously goes to infinity and instantaneously comes to 0 once again, right? At time t equals 0. So that is something which is extremely difficult to give in practice, okay? So then the question becomes, like what approximations can we get? Is there any other method to figure out the transfer functions and so on, right? So that we will learn as we progress, okay? There is another method by which we can experimentally determine transfer functions, which is by using what is called as a frequency response, okay? So we would learn that technique also, okay? So at the end of the course, like we will once again revisit the big picture. We will see that in practice, in practical problems, I will also share some case studies of research we have been doing on practical problems. You will see that at the end of the day, if you want to figure out a plant transfer function, it's going to be a mix of both approaches, okay? See, for example, we are going to derive using physics some equations and we will take Laplace transform and get the transfer function. But in real life, like it's going to be a mix of deriving equations based on physics and also performing experiments and using experimental data to fit the transfer function, okay? We need both approaches, okay? So we'll look at both approaches as we go in this course, right? But this is something which is very important, right? So you perform one experiment, you can get the transfer function. But the challenge in this aspect is that how do you get the ideal impulse input, right? That's going to be the challenge here, right? So yeah, so that is the impulse response function, okay? So this is as far as the definition of the transfer function is concerned, okay? So once again, this is extremely important, okay? Like as far as the definition of transfer function is concerned, right? So that is, we need to keep all initial conditions to be 0, okay? So then only, like we can essentially talk about transfer functions and use them, okay?